Hello, everyone. This is Ashley Childress with the Statistics Division of ASQ. I would like to welcome you and thank you for joining us today. The title of today's webinar is Definitive Screening Design, Characteristics, and Analysis Methods. Our speaker is Wayne Adams. Wayne is a
Hello.
consultant with StatEase Incorporated. His prior work experience included actuarial forecasting for a small life insurance plan, as well as the application of statistical techniques while working as a finance specialist for the Army Finance Corps. Wayne also taught business statistics at Western Michigan University, where he earned the highest student rating of all instructors. Wayne is now putting his statistical skills and cheerful personality to use in a variety of areas at StatEase. All phones and microphones other than the presenters have been muted, so if you have any questions or comments during the webinar, please use the questions interface in the GoToWebinar panel. Time willing, these will be answered at the end of the presentation. So at this time, I'm going to hand things over to you, Wayne. Thank you again for presenting today.
No problem. Thank you, Ashley. All right. Hello and welcome to everybody. I'm Wayne Adams. You can see my beautiful picture over there on the right. And as Ashley said, if you have any questions that come up later, feel free to contact me at my email address here at StatEase, wayne@statease.com. That will work just fine. So StatEase is a provider of DOE software and training and consulting. Founded in 1982 in Minneapolis, Minnesota, near the University of Minnesota. We have over a dozen professionals, plus a worldwide network of resellers. And our mission is statistics made easy, specifically design of experiments made easy. We've been honored multiple times by the ASQ, the Chemical and Process Industries Division, with the Schul Award, recognizing excellence in our presentation, scientific quality, and applicability. So what I want to be talking about today is screening designs, specifically the definitive screening designs that were brought out recently. So the concept of screening is to discover the few primary factors that drive your process. And then the problem is generally that there are too many potential factors to consider in a full-blown response surface type design. It's be too many runs, you'd never get it done. Screening takes advantage of a few assumptions. One is that the systems are dominated by linear effects, one factor at a time effects. Only a few terms from the full quadratic model are necessary to approximate the true response surface, and that third and higher order terms are generally not necessary over reasonable factor ranges. You don't need to model the wavy if you're all on the top of the mountain. Typically, screening designs have main effects uncorrelated with other main effects and the second order effects. This allows us to get clean estimates of what's going on one factor at a time, even though there's multiple factors being studied simultaneously. When you have two-level screening designs, the factors survive screening based on their main effects alone. If it's a significant or substantial main effect, it's included for the next phase of the experiment. When you have a large enough two-level factorial design, you can actually get at some of the two-factor interactions. And if you add center points, you can estimate a curvature term that will let you look at, is there going to be those quadratic effects? The definitive screening designs, abbreviated DSD, can address the possibility of those two-factor interactions and quadratics effects without any additional runs, and that's why I like them. So some of the details of the DSD. It was published in 2011 by Jones and Noxheim. Some of you have met these folks. And there were some modifications proposed by Dennis Lin in 2012 to use orthogonal conference matrices rather than optimal designs. And those circumference matrices have some interesting properties. First one is they always have an even number of rows and columns. The standard order for C is such that the diagonal elements are 0 and the off-diagonal elements are -1 or +1 in terms of the coded settings of the factors. And you can check to make sure you've got the right kind of conference matrix by applying C transpose C, and you should end up with M minus 1 times I, the identity matrix. Otherwise, you've got the wrong C matrix. And there's extra rows and columns that are added to allow for two-level categoric factors. Now the conference matrix is combined with its foldover and a center point to make the DSD. There's 2m plus 1 runs in the base DSD. The runs are randomized, and you can restrict the randomization by including some blocking. So they screen because the estimates of linear effects for numeric factors are indeed uncorrelated with the other linear effects or the second order effects. You can get good estimates of all of the one factor at a time effects. When you have categoric factors, there's some minor correlation with the other linear effects, but it's very minor. The design has the ability to fit the full quadratic model for subsets of any 3 factors for smaller ones. Once you get to 18 factors, it can fit 4 subsets of 4, and once you get to 24 factors, you get subsets of 5. So what that results in is when you have something like 11 factors, it'll project down to 3 factors and make a pretty good 3-factor design. So an example. This is an example. This is based on an example that we've had in our training materials for several years. The story goes, I wanted to incorporate DSDs in this example to see how it would work and how we could learn from it and make some new training material. There are 11 total factors, and there's 4 of them that end up being substantial and significant for maximizing the strength of the weld. And like I said, after reading about the successes achieved with DSDs, I wanted to see, could I use them? Could I make some new training material? From a model that I obtained from a central composite design, you get a response surface that looks something like this based on this model over on the left. This one's using a high substrate, the SS41 substrate, and a high current. The predictions when you use the different substrate and a low current. Trying to maximize, which one would you choose? Now if I take the model obtained from the CCD and I added normal 1000 variation to it, I created some data for a 26-run 11-factor DSD, and if I force the terms that I got from the central composite design model, I get a pretty good estimate of that model, even though there's 1,000 extra noise. They're not identical models, obviously, but they're close to each other, and they give you basically the same information. Somewhere in the middle angle, somewhere in the middle substrate thickness will maximize your response. This is essentially what you would get if you ran 2 separate experiments anyway. Problem is, how many of you know which terms are going to be in your model before you start the experiment? Some of you do, and that's a good thing. But the problem comes from how do you get the correct terms picked? Now there's several sources out there that recommend using forward selection using the AKE information criterion that's corrected for small samples, AICC for short. And AICC with the forward selection, adding 1 term at a time if it improves the AICC score, it's a good place to start. but we don't always get a useful model out of it. So let's look at some of the model fitting techniques that we can apply and use here. We know that linear effect estimates are orthogonal to each other and the second order effects. We can estimate all of them. And if you analyze the linear model, that's a good first step. Going through that, the B, J, and K factors turned out to have large enough effects to survive screening. And historically, this is where much of the screening work transitions to characterization and/or optimization. We also know that as with any screening design, a DSD can reveal second-order effects when you have only a few factors that are active, also known as sparsity of effects, and effects are large relative to the noise. So let's include some second-order terms. Based on some heredity principles, we can fit the terms from the second-order model, taking into account all of the important linear effects. So that makes us start with a quadratic model for those three factors. And when we use the AICC criterion to build it up, we end up including all of those three main effects that we found, plus a quadratic effect in J. Is this the correct model is the question. So if you look at a plot of the predictions versus the actuals, keep in mind there's 1,000 noise in here that's unexplained. We get a reasonable fit to the data. The problem is the model should fit the surface. So when you compare these two models, I'm looking at the A and B factors again. It's predicting the data, as you can see in the lower right-hand corners of those 3D graphs. But is the VJK quadratic model from the DSD the right model here? Even though it fits the data, we don't really have enough runs to identify the true model unless that sparsity of effects system is actually true. And we don't have enough information available to detect model misspecification. If you fit the wrong model and it fits the data, it fits the data. Optimum settings have to be near those design points for an optimization algorithm to find them. What's going on here is when there are second-order effects, they're partially aliased with the other second-order effects. Warning, wall of text coming. Partial aliasing is a system where there are several effects with coefficients attached to them that add up to be other effects. So what we're calling J squared is really the estimate for J squared plus a little bit of the AB interaction plus a little bit of the AK interaction. And I've highlighted the ones in red because those were identified in that original central composite design model. So when you look at it, the coefficient that we get for the J squared term is this 3,900 in rough terms. If we then look at the forced coefficients model that we fit from the DSD that I showed you on page 14, we get these coefficients. When you multiply those coefficients times the aliasing coefficients that we get off that partial aliasing list, we end up with these products, and when you sum them up, you get J squared that's really all of these put together. What that means is j squared isn't as important as we might have thought by fitting that BJK quadratic model. And this is where we run into those problems with the analysis that don't always get reported. So another method that gets talked about is trying the full quadratic model. That means you have 11 linear, 165 two-factor interactions, and 11 quadratic effects. When you build the model up with forward selection, you get a model that looks something like this. Now with the different simulation, you get a slightly different model terms and different aliasing structures come out. Long and short, we get pretty good identification of those same 3 linear effects. But now we fit an entirely different second order. And j squared's not part of this model. That tells me something's up with at least one of the models. This bigger model isn't sparse. There's 6 additional factors added. We've already talked about how the DSDs can fit up to 3 additional when it's 11 factors. Now I've got 6. I'm questioning this model. And what's going on is we're asking too much of the design. Because we have some terms that can be magnified due to partial aliasing. In the BJK quadratic model, j squared was magnified. Those interactions with A. In the full quadratic model, d squared was magnified. Its coefficient was 6,000 something. And it's coming from the combination of the j squared and all the AKs and all of those misspecified second order effects. And some terms can also be diminished due to partial aliasing, such as the j squared that got absorbed when we fit that full quadratic model. We also missed the A factor entirely by both modeling methods. However, this is a hidden cost of screening in general. We're running a smaller design. We don't have the power to detect the smaller effects. Plus, A is mostly important because of its interactions. The nice thing is partial aliasing has no effect on the uncorrelated effects, so we get the linear models. And we can make some basic decisions that way. Now, on the front of alternative approaches, consider not including every possible factor. Think about it using what you already know about the process. You only want to include factors that have unknown but possibly interesting effects in a screening design. You hold these known factors out until a later phase of the experiment. When you leave out the known factors, it reduces the number of effects that need to be estimated and reduces the number of runs required in the screening design. And you use the screening design to get those unknown factors that show significant, substantial effects, and you bring them back together with the known factors for the second phase of the experiment. So if we get into this experiment knowing that the current and the type of substrate used would be important to the tensile strength of the welds, we could leave them out of the screening design. We would go for a definitive screening design of 9 factors and 22 runs. There's still one categoric factor in there. And we'd have to make some arbitrary choices for the old J and K. For instance, we could use the center of the current setting, the amps that are being used, and we could choose to use the SS35 substrate. That's either SS35 or SS41, excuse me. And if we build up the linear model using that same AICC with the forward selection method, we would reveal that A and B are the active factors. And this is one of those examples where if we continued with that second order model, we would actually get good estimates of the true second order model from this DSD. We'd be expanding what we know. So my proposal is that we use the DSD as a good screening design. I like them. They have those built-in second order detections. Get it down to 22 runs instead of the 26 for 11. Retain 2 or more of the factors out of that good list of 9 now. And then we can add those 2 known factors back in and complete the next phase of the experiment. Now the reason I like this is we're at the point where we have a bunch of unknown factors, a model that fits the data but might not necessarily be the model. And if you want some assurances that you've got the current model, you'd need to augment the existing 11-factor DSD anyway. In that case, we would be doing this new design for the full quadratic model so that we could understand how these 4 factors that survive screening or subject matter knowledge, and we'd understand how they optimize together. If you're sure you don't have quadratic effects, then you can build this design for the interaction models. Save yourself some runs, depends on what you know about your process. So some of the conclusions, and then we'll open it up for the questions. The DSDs work very well for screening. I'm at the point where I really like them and recommend them for screening at this point. Linear effects are readily identified, and you can detect whether or not you have second-order effects. I'm a little bit cautious about using the models for optimization, and it's because of these second-order effects. We still don't understand them even from the DSD if there's enough of them truly active. And we don't know at this point, unless you're one of those people that knows your models going into the experiment. Consider augmenting these designs to truly understand what's going on and get the right optimization results. So thank you for paying attention to my short webinar. Made some important points about that the second order effects aren't readily identified, although we identify their existence. And that's the important thing about the DSD is they're screening those second order effects in addition to the main effects. So if you have any questions for me, feel free to type them into the questions box. We have plenty of time on this. And we will take it from there. Now, one question came in about the unknown factors and whether or not we need to look for the interactions between them and the known factors. Potentially, yes. But that means we're at the point of if we include them and we do that 11 factors and have all of those, and we end up with 4 factors in the second order effects for this design, we can't identify which second order effects are really there. We saw J squared come up. We saw the CE, that very long full quadratic model with the 6 extra factors. We don't know which one's correct. is the issue. Another question is, if we're creating a DOE class for engineers, what types of screening designs would I include? Only DSDs. You always run into the problem of build a design for your problem. Don't force your problem into a design. It depends on what you know. I mean, DSDs, I start there with my thinking. I'll go with that. But we also have the typical two-level factorials, resolution 4 factorials, there's some min-run, there's some optimum designs that will all work. You can also screen with full factorials, where we can get at all the interactions. Might be necessary in cases where you have low power. Small effects are essential to detect. The screening designs might be too small, and you're forced into those bigger designs. So it's an it depends question, most definitely. True replication in the DSDs. Center points can be added, but you have to really watch how you're adding them, because it can make the design start to go on non-orthogonal and start to get some correlations that you were hoping not to achieve. And that's one of the nice properties of the DSDs going up front. And that is one of my downsides to it. They don't have the built-in, but the center points can be augmented, adding extra center points. The other question that came in is, when I ran the second DSD with the 4 factors, it actually had 9 factors, and I used that same model, but I used fixed values for J and K, which shrinks the model down to just the 2 for the A-B interaction and quadratic effects. But it was the full 9-factor DSD. I fit the linear model first and then expanded to the second order model. When I fit the model. The $1,000 question. What is the good indicator for a model to be considered a good model? Fits the data, and you can look at that through various statistics on analysis of variance. Your R-squared statistics are a good place to go. The diagnostics back that up. But as I showed, fitting the data isn't enough. And that's one of my issues with the definitive screening designs, is quite often those quadratic effects sneak in there because that's the simplest model that fits the data, but it's not the model that fits the surface often. And that's the tough call, making the decision from data alone. I'm not sure it's possible. And that's one of the reasons I put this presentation together. And augmenting the DSD. You can augment your DSD if you haven't dropped any factors. The issue with that, of course, is all those other variables that varied. Are you going to vary them in the augment as well? If you're dropping them because they didn't survive screening, the goal of that is to drop it down and learn something about the truly active effects now. If you're sure about some of the interactions, you want to add them in. Of course, you can always build your designs to that standard. You know, design for the model you believe is true, or you want to check. Either way. And then the recommendations when nominal variables are included. The nominal variables or categorical variables is another way to talk about that. Is when they're DSDs, they have to be two-level. There's a blog. If you go out to this website here, page 35 of the presentation, that blog goes over some of the limitations when you're adding the categoric factors. They have to be two-level. They don't work quite so well when they're three-level. And the idea of model averaging also comes in. Fit a bunch of models, and then try to, and then confirm your results from those. And that works pretty well as on top of things. And the difference between Taguchis and DSDs, they're actually pretty well related. The DSD is actually more related to Plackett-Berman designs. But the Taguchi designs have those orthogonal arrays. They're not really suited to detecting quadratic effects. You know, you can use your linear graphs to try and come up with things, but they still suffer from that problem of aliasing. But they're typically resolution 3 designs where the main effects are correlated with the second order effects. Not always, but most of those orthogonal arrays actually do end up having aliasing between the main effects and the second order effects, where the DSDs do not. The DSD is more than simply a way of identifying the main factors. That sells it short from what it can do. It can be used for optimization, and it does detect those second order effects. But true identification and estimation of those second order effects depends on there being only a few effects that are actually active in the second order terms, few factors active in the second order terms, and there not being a lot of noise, because that will cover them as they would in any small design. But that is one of the decision points of when you do screening designs. You're trying to reduce the number of runs and study many factors and reduce them down. There are other methods of analysis besides AICC with forward selection. It's being studied by all of us in the business, if you will. Limited results is what I've been seeing, and I'm finding them difficult to analyze at the second order level. But at the first order level, I trust them. Any more questions?
Okay, if there are no more questions, we'll go ahead and end the presentation. Thanks, Wayne. That was a great presentation. We ask that our attendees complete this short survey at this time, available within GoToWebinar. A recording of the webinar will be available within a few days on the division's YouTube channel. That website is youtube.com/ASQStatsDivision. Please be sure to share this webinar and our other archived webinars with friends, coworkers, and colleagues. Also, we encourage you to check out the division's LinkedIn page, as well as our events calendar, which can be viewed at asq.org/statistics for the latest news on webinars, conferences, and many other topics. So that's all the time we have today. Thanks everyone for joining us, and thank you again, Wayne, for presenting with the Statistics Division. I hope everyone has a wonderful afternoon.
Thank you very much.